Today we're going to talk about one-on-one and inverse functions. First of all, we need to go back and define what is really a function. And a function is a relation in which each element of the domain corresponds with exactly one element of the range, which may or may not mean something to you. So in maybe a little bit simpler terms, what that means is that every x value has exactly one y value, and maybe even in simpler terms, no x value can repeat. We can use the vertical line test to determine whether something's whether a relation is a function if we've got a picture of a graph. And what happens here is if we draw any vertical line, and I'm going to erase these vertical lines, but if we draw any vertical line in this graph, and it ever crosses the graph more than once, then we say that this is not a function. What you can see in this picture here is this specific line. We've got x, y1, and we have x, y2. We've got an x value that repeats, and therefore it is not a function. And that's what it says. Here's why it works. If a vertical line passes through a graph at more than one point, there is more than one value in the range that corresponds to one value in the domain. The x's repeat, it's not a function. Number 3, a function, f of x, is called one-to-one if x sub 1 doesn't equal x sub 2, implies that f of x sub 1 doesn't equal f of x sub 2. That's a hard math definition to read, so again, let me put it in different words. Different inputs, which are the x values, give different outputs. In other words, no x value will repeat, and neither will any y value. A y value can't repeat. No x's repeat, no y's repeat for something to be one-to-one. When we have a picture, we can tell whether a function is going to be one-to-one by using the horizontal line test. And it works the same way that the vertical line test works. If ever, and again I'm going to erase this, but if ever any horizontal line ever touches the graph more than once, then our function is not one-to-one. So in this particular case, what happens over here is this is not one-to-one, because we have x sub 1h on our graph, and we have x sub 2h on our graph, but this time the h's, which are in the y position of the order pair, they repeat, and we cannot have any repeats, either x's or y's repeat, when we get a one-to-one function. If a relation is a function, and it is one-to-one, then we can find the inverse. Down here in 5a, and we'll get to it a little bit later here, there will be times, however, when we restrict the domain of the function so that we create a one-to-one function so that we can find the inverse, and we will do those later on in these notes. This here. So we want to determine if the relation is a function. Remember, we can use the vertical line test to determine if a relation is a function. And it says to sketch the graph, but we don't really know how to graph x cubed minus 3x without with our parent function. So let's type it into our calculator. So we can go to y equals, and we type in x cubed minus 3x, and we hit graph. And the only reason is so that we have somewhat of an accurate sketch to draw in here. Roughly, it looks something like that. So the first question is this a function? In the vertical line test, I don't want to draw through it because I won't be able to erase it. But is there any vertical line that ever touches that graph more than once? No. So that means that it is a function. And then the question is it 1 to 1? Well, to determine whether something's 1 to 1, we use the horizontal line test. Again, I don't want to graffiti this up. But if we draw any horizontal line, will we ever cross the graph more than once? Yes, and because of that, it is not 1 to 1. Vertical line to determine whether it's a function. Horizontal line to determine whether it's 1 to 1. Number 2. F of x equals the cubed root of x. It's one of our parent functions. Looks roughly like that. So I give it away, so to speak, because I said, well, the cubed root of x is one of our parent functions. Is it a function? Yes. We don't even need to draw any vertical lines in there. Is it 1 to 1? Yes. Even though it kind of looks like I have a horizontal line up here at the top of my graph, I don't. It's continuing to go up, so it's also 1 to 1. This third graph here, we may need to type into our calculator, although remember that the negative in front of the function means that we're going to reflect our graph over the x, and the plus 3 means that we're going to move our graph left 3. But just to be sure, we can hit alpha y equals, and we can type in negative 1 over x plus 3. Again, remember, our goal in this unit is not to use the calculator too much. But we're just getting a rough sketch, and here it is. And then look at the picture again. Yep. Something like that. Is this a function? Yes, it still passes the vertical line test. There's no vertical line that ever touches that graph more than once. Is it 1 to 1? And it also is 1 to 1. It passes the horizontal line test. So we've got the basics from the front of our notes. And we're going to digress here. We're still mostly talking about some ideas that we learned in Algebra 2, but we may have forgotten over the course of time. So if we find the inverse of the function, if a function is a set of ordered pairs x, y, then the inverse of the function, denoted with f to the negative 1. F to the negative 1, all that means is inverse, is the set of ordered pairs yx. In other words, when we take a look at these, our function 1, 1, 2, 8, 3, 27, well, the inverse of that happens when we switch 1 and 1, which doesn't make any difference. They still look the same. 2, 8 becomes 8, 2. And 3, 27 becomes 27, 3. The inverse. The x and the y switch places. They reverse order. When we're finding the domain of this function, of the original function, the domain are going to be the x values. 1 and 2 and 3. And the range are going to be the y values of the function. 1 and 8 and 27. When we look at the domain of the inverse are going to be the x values of the list of our ordered pairs. which are 1 and 8 and 27. And our range is going to be the y values, which are 1 and 2 and 3. And that's what we see right here. In general, if a function is one-to-one, the domain of f is the range of our inverse. And the range of f is the domain of our inverse. Again, if the x's and the y's switch places, then the domains and the ranges are going to switch places too. Now, I've got the box here on the same page as our domain of f equals the range of the inverse and vice versa. There's also a theorem that we're going to utilize here on our next example, which says that the graph of a function and the graph of its inverse are symmetric with respect to the line y equals x. So let's take a look at that problem here. And it's the same kind of thing. Let's graph here. It says graph the function and its inverse. So if we start here with -3, -1, -1, 0, 2, 1, and 4, 3. It says graph the function and its inverse, connect the points in the order that they're given. So if we connect we get roughly a picture like that. To find the inverse, we need to switch the x's and the y's. So -3, -1 becomes -1, -3. -1, 0 becomes 0, -1. And 2, 1 becomes 1, 2. And 4, 3 becomes 3, 4. Again, we're going to graph those, and we're going to connect those points in the order that they're given. So we have -1, -3. 0, -1. 1, 2. And 3, 4. -1, -3. Over 0, down 1. 1, 2, which is over 1, up 2. Connect them in that order. And once I have that 1-point graph correctly, it makes a big difference. And now what it says to do is it says graph the line y equals x. Well, our line y equals x goes from the lower left-hand corner to the upper right-hand corner, going through the point 0, 0. It is one of our parent functions that we learned. I usually graph it with a dotted line. It just depends on your teacher. We graph the line y equals x, and what do you notice? If anything. The points are reflected. Over the line. equals x. So what does that mean? And before I talk about it so people watching the video can understand, it's this point goes with this point. And this point would land on that point. And this point would land on that point. And this point would land on that point if we folded this graph along the dotted line. In other words, for people watching the video, we have the point -1, -3. When we fold it along the blue line, that -1, -3 would end up to be -3, -1. Or the point 0, -1, when we folded, would land over here at -1, 0. Or 2, 1 would land on 1, 2, and so forth. That's what the reflection. Folded along the dotted line, and the black graph lands on the red graph, or the red graph lands on the black graph. But let's take it a little step further. Now that we kind of have the idea of inverses in our mind, let's find some inverses algebraically. And these are the steps that we use. We replace the function notation, f of x, g of x, with y. We switch x and y in the equation, just like we did with the ordered pairs. Then we're going to solve for a new y to find the inverse. And then we're going to label it appropriately with our notation, f to the -1 of x, or whatever the name of the function was. So some good steps to keep in mind as we take a look here at our first picture. It says find the inverse of f of x equals 3x plus 6. We need to graph the function and its inverse along with the line y equals x. And let's actually just start back there and take it one step at a time. So first things first. First step in our steps that we just talked about in our boxes. Instead of writing f of x, let's write y equals 3x plus 6. Second step. Switch the x and the y. Nothing else. Only the x and the y change places. So x goes here and y goes there. Nothing else changes. The 3 doesn't move, the 6 doesn't move. Third step. Solve for y. So we're going to subtract 6 on both sides. We'll get x minus 6 equals 3y. And then we're going to divide everything by 3. Because we're putting this line back into slope-intercept form, so we end up with y equals x over 3 minus 2. And don't forget that the number in front of the x is 1. So what we just did is we found the inverse. Our last step is finding the inverse is to put it in the proper notation. So actually let me draw an arrow here. So our inverse here, it's f to the -1 of x equals 1x over 3 minus 2. So we found the inverse. Now we need to graph the function and the inverse. Well, what's the y-intercept of our blue equation, also abbreviated as v? 6. And what's our slope? Well, it's 3 over 1. It's the coefficient on the x. So when we come over here to our graph, b equals 6, and then our slope is up 3 to the right 1, or we can go down 3 to the left 1. Here's our function. We can also graph the green line. But we have to identify what's the y-intercept and what's the slope of the green line. What's the y-intercept? Well, it's -2. Our slope is 1/3. So here's -2. And then rise 1, run 3. Up 1, to the right 3, up 1, to the right 3. Go down 1, to the left 3. By the way, it just so happens that our graphs do intersect, but they don't have to. So we graph the function. We've just graphed the inverse here in the green. And then we also need to graph the line y equals x. Well, once again, that parent function, y equals x, goes from the lower left-hand corner to the upper right-hand corner through 0, 0. There's y equals x. And you can kind of look at that and think, if we fold this graph where the red dotted line is, will the green line land on the blue, or will the blue line land on the green? And it looks like it. We have to stretch it a little bit. But 0, -2 has a point of -2, 0. 3, -1 has a point of -1, 3. And so forth. You can look at the points across that red line, and you'll see that they are reflected. So finally, and maybe the hardest part, is what's the domain of our blue line? And for whatever reason, that might be the hardest. But it is -infinity to infinity. And as we pointed out a couple minutes ago, the domain of the function is the same as the range of the inverse. Not only is the domain of the function all real numbers, which is -infinity to infinity, but any line with a slant has domain and range of all reals. And if we can identify the range of our original function, then the range of our original function is the same here as our domain of our inverse. But earlier on, we talked about how, well, let's look at the problem. Find the equation of the inverse of f of x equals x squared plus 3 if x is greater than or equal to 0. We want to graph the function and its inverse along with the line y equals x, label each function, state the domain and the range of each function. And earlier on, what I started to say, earlier on, we had talked about how if something isn't one-to-one, isn't a one-to-one function, then it's hard to find the inverse. So what happens here, notice the part that says if x is greater than or equal to 0. Well, first of all, That's the domain of the original function. And the first question is, well, what would the graph look like if we didn't restrict the domain? And what the graph would look like if we didn't restrict the domain is it looks like a quadratic. And we would not be able to find the inverse of this because this function is not one-to-one. We have a point there and a point there. It fails the horizontal line test. It passes the vertical line test, but it fails the horizontal line test. But the nice part about this is, given that domain, which is x is greater than or equal to 0, we can fill it in right now. 0 to infinity is our domain. And if we're really thinking about it, and I will fill it in eventually, but if you're really thinking about it, you can fill in one more blank right now. But we'll fill it in eventually. Now, remember that domain deals with the x values. And I'm going to erase, so if you're writing in pen, wait a couple minutes before you write this down. Plus 3 on our x squared, on our square function, means that we're going to move the graph up 3. So this graph, without restricting the domain, would have the points 0, 3, 1, 4, and then 2, 7. Also negative 1, 4, and negative 2, 7. Again, don't write this down if you're writing in pen, because I'm going to erase. That would be that picture of the graph, x squared plus 3, without x is greater than or equal to 0. Well, x is greater than or equal to 0 means that we are not going to deal with anything over here. We're only going to deal with that part of the graph. Starting at the origin and going to the right, greater than or equal to 0. Now this function is one-to-one, along with being a function. And when it's one-to-one in a function, then we can find the inverse. We're going to follow the steps in our box. And those were that instead of writing f of x, we're going to write y equals x squared plus 3. Switch the x and the y. Switch the domain and the range. So x is going to go where y went. Y goes where x went. Notice the squared didn't move. The plus 3 didn't move. That's our second step. Our third step is to solve for y. So we're going to subtract 3 from both sides. And we get x minus 3 equals y squared. To solve y squared so that we just have y, we're going to take the square root of both. So we end up with y equals the square root of x minus 3. And if we write that with inverse notation, then this is going to be f to the negative 1 of x equals the square root of x minus 3. Our parent function would be the square root of x. And then we're subtracting 3, which means that we're going to go, thank you, right, 3. Which would make sense, because if we have this point 0, 2 on our graph, then we better have the point 20 on our graph. And it might be nice if I read my graph a little bit better. If we have this point 0.03 on the graph, then we better have the point 30 on the graph. There's the right 3. And then there was only the one transformation. Seven, 2 is also on our graph. And let me say those points again. We have 3, 0, 4, 1, and 7, 2. By the way, I did stick with positive values. Technically, when you take the square root of something, like you take the square root of 4, square root of 4 is not only 2, but negative 2. But because x was greater than or equal to 0, I left it with our positive values here. So we've graphed our function. Here's the function in red. We graphed our inverse. That's in black. Which I can't write. One more time, I'll try. And then we also want to graph the line y equals x, because these two pictures should be reflections of each other. So we're going to graph the line y equals x. And if we think about it, if we fold this graph along that blue dotted line, the black graph will land exactly on the red graph. Like I said originally, 0, 3, we better have 3, 0. 4, 1, better have 1, 4. 7, 2, better have a 2, 7. And we do. And now we have to come over here and we have to fill in the domain and the range of each of these functions. But the good news is that the domain of the function was given to us already. And if we know the domain of our function, then we can figure out our range because they're the same. Again, the reminder, domain are dealing with the x values of the function. Range are dealing with the y values. So on our black graph, 0 is our lowest point. So range, the range of our function is going to deal with the y's. Looking at a red graph, the range is going from the lowest point in this case to the highest point. What's the lowest y value? At least think it in your mind. Our lowest y value is 3. And then the graph continues up. So it's going to be 3 to infinity. And does that make sense when we look at it, our inverse over here for our domain? Is the point farthest to the left in our graph 3? And it is. And there's our domain and range to go with our picture. So what we've been working with primarily today is working with graphs and identifying the domain and the range of both the function and its inverse. But what if we're just given an equation? Well, we can still find the domain of the function. We can still find the inverse of the function, and we've been doing that with our graphs. That's the nice part on problem number 3, is that we don't have to draw the picture. We will eventually put it in our calculator. But we need to go back for a couple minutes and think about, how do we find the domain from an equation? And to find the domain from an equation, what we do is we take the denominator. In this case, since it's a fraction, we're going to take the denominator, only the denominator, and we set it not equal to 0. If x plus 2 doesn't equal 0, and then we can solve. Subtract 2 from both sides, get x doesn't equal -2. And the graphics over here are helpful, yet again, to reinforce this idea behind domain and range. But what we just found is the domain of our function. And it's that x doesn't equal -2. And by the way, MathXL lets you write it like that. So we can all breathe a sigh of relief for that. X does not equal -2. And if we know that the domain of our function is x doesn't equal -2, remember that has a relationship to the range of the inverse. The one thing that we need to be careful with is that range, remember, is representing the y values of the function. So down here, domain draws the arrow to the range. This is y doesn't equal -2. Well, that's all we can do so far for that part, for the domain. We found the domain of the original function. Now what we're going to go ahead and do is we're going to find the inverse. And the difference on this one compared to the previous problems is we had 2 x's in here. But that's okay. And our first step says that we're, instead of writing h of x, we're going to write y. The second step says that we switch the x and the y. So x is going to go where y went, y is going to go wherever x is. So this is going to be x equals 3y over y plus 2. The x's and the y's switch places. They reversed order. Well, we've had some experience solving this now, because what we're going to do is we're going to cross multiply. And we end up with x times y plus 2 equals 3y times 1. And we can distribute here. We end up with x, y, plus 2x equals 3y. And what we're trying to do here in step 3 is we need to solve for y. But we've got a y on the left side, and we have a y on the right side that we need to deal with. So first of all, let's put them on the same side of the equals. So let's subtract xy from both sides. So we get 2x equals 3y minus xy. How are we going to get y by itself? Carolyn? We cannot divide them. Good try.
Not the y side,
Kind of. Before we can divide, we need to factor out the y. So you might have gotten it. If we factor out the y, then there's only one y now written in the equation. We're trying to solve for y. That's our third step. When we solve for y, we'll divide by 3 minus x. So hopefully you didn't have to squeeze it in. I was lucky enough that I can keep sliding this down here. The 3 minus x's cancel out. And we have y equals 2x divided by 3 minus x, which, by the way, is our inverse, and I think I'm dealing with h this time. I am. h to the negative 1 of x. To finish this problem, even though I'm running out of time for graphing, but to finish this problem now, what we have to come up with is, what's the domain of the inverse? Well, just like the original problem, what we did is we took the denominator and we set it not equal to 0. We're going to take the denominator, 3 minus x, and we'll set it not equal to 0. We can add x to both sides, and we end up with x doesn't equal 3. That's the domain of this function. Which if we go back up here to our box here, we can say x doesn't equal 3. But look at the graphics here. The domain of the inverse goes back to the range. Remember that range is represented by y. And y doesn't equal 3. Well, look at it